BSUG. Today we have Amir Nizamdoost and Alan Mahich. So they're going to talk to us today about blind control patterns and the impact that including or not including blinds can have on a building simulation. Amir is one of our MArch students, so Master's of Architecture, and he's been here 1 year now?
1.5.
1.5 years at the IDL. Alan is a graduate from the U of I, and he's and he's been with us for about 3 years. He does a lot of our daylight simulation and scripting for us. So they're going to talk to you about the blinds, and then feel free to answer questions at any time. Take it away.
Thank you, Katie. So thank you everybody for coming. This is the annual energy and daylight impacts of blind controlled patterns through simulation. So let's first start with the review. Why do we need blinds? Basically, we have two strategies in daylighting design: top lighting strategy and side lighting strategy. In side lighting strategies, mainly we use the windows, and windows play the main role in side lighting strategies. And architects love windows. There is no harder thing that to have to compose an elevation for a building that has no windows. We get somewhat lost in these situations. The main thing about the windows is the view. There is a good reason architects love windows, and it's the same reason why people love windows. Daylight and views to the outdoor are a powerful draw. While most people spend the majority of their life indoors, we crave that connection to the natural world that sunlight brings. It's more than just vitamin D. The pull of a view outside and access to daylight is built into our psyche. But the issue is how to manage direct sun from the windows. And why do we need to simulate blinds in our models? The first thing and the main thing is glare and visual comfort. Because when I sit on that desk and I have that direct solar in front of me, I feel uncomfortable and unproductive. And I'm not productive. So we need that in our model. And we don't want to be in her shoes with shading, use our hands as a shading. And if architects do not predict blinds in their building, people will do like that. The other thing that we need to simulate blinds in our model is the heat gain. Shading inside the building envelope make reductions based on HVAC cooling loads, and depending on shade material, the shadings reject up to 75% of solar heat gain. But there is another issue. Our design intent is to blinds open in a good condition and lights dim. But the sad reality is occupants let the blinds close and lights on. So that's the issue that we have to notice about that in our simulation. And that's the reason that we waste 60% of electric lighting and 40% cooling saving when we let the blinds close and turn the lights on instead of using daylighting controls and changing the blinds. And so that's the reason we need some patterns based on people behavior, view preferences, glare, and privacy. You can see in this picture, we have south facade, and based on the high amount of direct sunlight, the blinds should be down, all of them. But you can see on the first floor, because of the privacy, windows are all closed. But on the third, fourth, and fifth floors, with higher amount of sun penetration depth and direct sunlight, most of the blinds are open. And that's because of the view. And on the north facade, you can see that windows all are always open. So, sorry. So we need. So there are three main blind control patterns right now. Blind switch A, blind switch B, which both of them proposed by Kevin Van den Wimmelenberg, and the third one is IS LM83. The blind switch A is based on penetration depths. Blind switch B is based on exterior vertical illuminance, and the LM83 is based on direct sunlight. Blind switch A. Blinds retract if direct solar falls below 120 watt per meter square on the window, or penetration depth falls below respective trigger for a specific duration. And there is a hysteresis for this blind switch, which is a time-based, and it controls retraction points for each window. Blind switch B is blinds engaged if vertical exterior illuminance is above a certain trigger limit, and hourly vertical exterior illuminance values were gathered using radiance results. The same as blind switch A, we have hysteresis, but this is lux-based, which is controls retraction points for each window. And LM83, blinds engage if more than 2% of the analysis area is receiving direct sunlight, which is 1,000 lux. And we have single bounce ray tracing using radiance to track direct sunlight only for each window group. And our grid within the space is 2 by 2 feet. Window groups are closed using a worst defender first logic until the area receiving direct sunlight falls below 2%. So what is the workflow? Each manual algorithm, blind switch A, B, and LM83 or automated pattern require unique simulation pathways to conduct an energy and daylighting study, but in all cases requires co-simulation between EnergyPlus and Radiance. And that's the main workflow that we are working on it for our manual blind controls patterns and automated patterns. Alan, do you want to go through that?
Sure, I think I can chime on that. Can you still hear me back there? Okay. So basically this is the portion where Amir and I kind of coordinate between the two of us. Amir does mostly the energy simulation portion, and I do most of the radiance simulation. So Amir would set up an energy model. He would generate an inclusion schedule for me to use in Radiance, and then I would feed him the actual daylight lux results so that he can generate a fractional lighting schedule for an energy run. That way we can compare operated blinds with open and always closed blinds as well.
So in EnergyPlus, first before we export our file into EnergyPlus, we set all the things the schedules, construction, loads, everything in OpenStudio. And just for adding the blinds, we export the IDL file and go to the text mode, and then use the window material shade for our model. This object specifies the properties of window shade materials, and the window shades can be inside the window, outside the window, or between the glass layers. Window material shade can be used for diffusing materials such as translucent roller shades, and for slat type shading devices, we can use the window material blind instead of window material shade. So this is the commands that we have to work in window material shade. That's the example. You can put the name at the first line, and you can assign solar transmittance, solar reflectance, visible transmittance, thermal transmittance, thickness, conductivity, shade to glass distance, that's the important part, and top opening multiplier, bottom opening multiplier, left side and right side. These four will be calculated based on this picture. You see, to calculate the multipliers, you have to find the ratio of the S, which is the gap between the blind, the shade, and the window, the glass, the ratio of the distance between shade and glass to the gap between shade and wall, right? Well, okay. So on the next step, we need window property shading control. Window shading with coverings like blinds, screens, pull-down shades can be used to reduce the amount of solar radiation entering the window or reduce daylighting glare. Also, if we want to model a case in which the shading device covers only part of the window, you will have to divide the window into two separate windows, one with shading device and one without it. And you have to put in the EnergyPlus. You can add as an interior shade, exterior shade, interior and exterior blind as a shading type, and you can put the name of shaded construction that I will explain it on the next slides for you. We have a bunch of shading control types that you can use them, and you can find them in input-output reference because there are a lot. And you can use the schedule name and use it as and assign it in a schedule shading control type that use that schedule name. And if we want to shading control a schedule, you can say yes. And if the glare control is important, you can put yes there. Also, we have a material name for shading device that I will explain on the next slides for you. And if you have a blind, slat type blinds, you need to assign those two last lines. So there are two methods to assign a shade to a window. The first method is to define a construction for a window. We can say that bare construction, and reference that construction to all the fenestration surfaces. Then we can define the window material shade and define the window property shading control for a window in which you want to specify window material shade. And that's the part you have to change according to the material you define for your model. And make sure that you don't have any shaded construction here. But for the second method, you can make two constructions. The first one, as a bare construction, you don't need to add any shading materials to that. But for the second one, that we can call it shaded construction, you can add your blind or shade as a last layer of your construction and name it as a shaded or anything else. But remember to use this name of the construction with shade. Here in your shading control with this name of shaded construction, and make sure that you don't need any material name for your shading device. And the last thing you need is energy management systems. The energy management systems is one of the control methods available in EnergyPlus. And EMS is able to access a wide variety of sensor data and use this data to direct various type of control actions. The EMS is one of the high-level control methods available in EnergyPlus, and EMS is able to access a wide variety of sensor data and use this data to direct various types of control actions. There are a bunch of EMS commands, and just I want to show you the important ones. And the energy management system program is the main EMS that we use to define our logic that how the blind operate. So,
All right, how does that sound, Katie? Still good? Okay, check. Okay, so I'm going to be covering some of the more details on the Radiance side and just how we approach to doing something like this. You could call it co-simulation, even though it's not per time step. We're kind of passing mass quantities of information between EnergyPlus and Radiance. But to start, to set up the model, we basically start from the OpenStudio energy model. It's usually the best method when you want a sealed model, which is usually not the case with Revit. So when we export and import with Revit, you have so many details that more often than not, you end up with gaps in the model. So when you put that into Radiance, that gives you light leaks, which causes some issues. And tracking those down and closing them can be quite a task. So we start with the OpenStudio energy model, and we can see a floor plan of it here. And then we add partitions as needed. And workstations, walls, that type of thing. So we kind of overlay what we need for the daylighting portion over the energy model itself. So the window groups are essentially set up as they would be in EnergyPlus to have some consistency between the schedules that are both output and input from one model to another. And we have blind operation would be based on the 4 zones that you see here. So we're looking at, obviously, this would be about 50,000 square foot floor plate of a multi-story office building, and we're excluding the core out of it, and then setting up these, I guess, simplistic daylight zones, but there's a specific reason we do that I will get into here in a second. So these are the actual grids that we set up for the entire building. So this was just one floor, and this actually gives you kind of an idea of what we're dealing with when it comes to simulating in Radiance. Okay, so when we set up the window groups, we want to make sure that the decisions being made by the algorithms or that the algorithms are operating off of the best information that we can. So when we try to operate all of these windows that go around based on this whole floor plan, we would have, for example, the north or even the northeast up here, the window groups being affected by what's happening down here in the south, which would be a bad decision, logically speaking. So when you split this up into zones, something like this, so the north and part of the east here would be operated by the points that you see in this particular zone. And then we would use that, pull the four zones together to actually get the proper blind conditions and then the light that they're contributing to the overall floor plate, the entire floor plate. And what we're looking at here is basically the daylight autonomy of this 50,000 square foot floor plate, and that would basically be the time or the percentage of time of occupied hours that that particular point is above 300 lux. And we can see the point here for reference. Okay, so exporting geometry out of SketchUp is our main tool here, but we can essentially work with any modeling software that can deal with OBJs. That's sort of our what we aim for. But SketchUp is nice in that it can go directly to RAD via a Ruby extension called SU2RAD, SketchUp to RAD. And essentially what we're seeing here are two samples. On this side we have a Radiance model, and over here we have an OBJ model. So essentially they're made up of coordinates, right? So it's pretty simple. We have corners that make up surfaces. So when we approach this from a scripting-based perspective, we can actually start to generate our own analysis grids, start to process some of these surfaces on our own. And this is something that we developed here at the lab that's similar to how Ecotech does it, minus the nice interface, obviously. Okay, so when we set up the model for Radiance, this would be the general bins that we put certain things into. So the grid that we were just looking at would essentially end up in its own bin, right? We have a data folder, and we set up our materials in its own, and we have our objects and windows kind of in two interconnected bins. And then down here we have the weather data. And then we pull all of that together, again via scripting, to basically create a Radiance model out of all the geometry that we borrowed from OpenStudio, in a sense. Okay, so this outlined essentially we have the how we would simulate this. So we have the four zones and we have the whole floor plate. So we would have, if we're looking at the entire building, we would have 691 window groups for each iteration of this model. So we have the separate zonal, the daylit zones, so 4 models, and then we have the whole floor plate. And what we do with this is essentially we generate a direct solar simulation to give us an idea of just how much direct sun is penetrating into the space. And then we apply that, or we operate our blinds based on each of those zones, and then we would apply the schedule to the whole floor plate, which would give us the full ambient calculations, you know, all the bounces and everything that's going on in space. So we would do this for 8760 hours, but as I'll get into it later, the Radiance simulation methods allow us to actually do this part in one step, which is nice. Otherwise, this would actually total out to that interesting number right there, which would be that many simulations to basically do everything that these two methods require, essentially. Okay, so another issue that we run into would be window grouping granularity. So we set up our window groups as they would be set up in an energy model, which is usually just window per window. But if we want to take into account something like a shading material, which isn't slat-based, it's actually, you know, how far up or how far down you're lowering it, then we have to start subdividing our geometry, right? 1/2, 4, 8. And you can see just how crazy that can get when you multiply the actual window groups by the divisions that we're doing here. So that's just one thing to kind of keep in mind, the scope of a project and just how much you can handle both computer-wise and person-wise as far as hours are concerned. So here's a quick example of the effects of window granularity. So we have a classroom with with 3 bay windows split down the middle. So we have a high bay and then the actual view windows. So what we're looking at here is if this space or this facade was treated as one window group, these would be the results. So over here we're seeing a DA, again the percentage of time that this area is above 300 lux for 50% of the time of the year at least. And then over here we have the direct sun simulation showing the area that is affected by direct sunlight for more than 250 hours out of the area, or out of the year, I'm sorry. So the next one here splits it. It splits it down that high bay versus view window. And we can see a pretty drastic change here. The light shelf probably has a little something to do with it, but we can see a pretty drastic difference both in the ambient penetration and the reduction in the direct sunlight. So the next step to this would be to split these into their 3 counterparts, which would give us 6 window groups. So it's not as much of a gain, but we still see sort of a slight shift over here, and then an actually pretty big shift for the ambient penetration. So 60, 54 to 60, pretty significant change there. Okay, so after the model is set up, this is essentially how we would approach the simulation. And the Radiance 3-phase method is essentially the best way currently, or I should say the fastest, to annually simulate dynamic and complex fenestration systems. And we break this down into 3 distinct phases, which I'll go into a little more detail on those. But it's basically the relationship of the exterior, the sky, to the outside of the window, the relationship of the interior to the inside of the window, and then the window itself. So those are 3 distinct pieces that we will put back together, essentially. So they're simulated separately and then multiplied and added together. So here's basically the breakdown. So we're seeing matrices, essentially. So we're turning a simulation model into coefficients that we can apply weather data to. So once we have these matrices, we can apply any number of weather files or EPW TMY3s as we want, basically. So we're running one simulation and then doing math after that. So the view matrix, again, this will be the interior to the inside of the window relationship. We can see here an example BSDF, which I will go over next. But we have shades closed on this side, and then shades open on this side. So we can see direct sun coming in, and then it's a lot darker on the projector. Kind of see it popping out there. So the actual transmission matrix, which would be this right here, the application to those surfaces, it basically describes the way that a particular system will reflect and transmit light through the actual window. And as far as radiance is concerned, we're only interested or mainly interested in the transmission portion because our points of observation are on the inside of the space generally. So whatever is coming in will be registered, and whatever is being reflected to the outside generally will not. But those are the 2 main pieces of it. And we can generate these using the LBNL Windows 7 software, where we can actually set up any number of layers that you would like. So in this case, we have a clear piece of glass, we have a solar band 60 Starfire, and then we have a shade. So this whole system gets exported as one single BSDF, which can be simulated something like this. So you don't see the shade, but its contribution is registered. That's the difference between these 2. Okay, and this is just the visualization. The BSDF by nature is, again, text form, just like Radiance would require as input. And these are the distributions of the BSDF given certain directions that light is entering the opposite side of the window. Okay, so to cover the daylight matrix just really quickly here, how we would approach this, instead of obviously doing 8760 different simulations for each time step, we would divide our sky into pieces, and then we would account for the contribution of each patch to the outside of that fenestration. And that would become a matrix, basically, a series of coefficients that you can multiply or add weather data to, or different sets of weather data to. So here's an example, false colors. So if we render these skies in radiance, we're seeing here the classic smooth, a continuous sky that you would get if you just generated a sky in radiance. Over here we have the Tregenza, Reinhardt, 147, 577, and 2600 divisions. So what we're seeing here is you can barely make out the sun disk here, which is what we're after. You want that disk to be as small as possible. When it's this big, the intensity gets spread across a larger area of the sky, which means the peaks are going to be more inaccurate. But again, we have to trade some accuracy for speed, basically, when it comes to simulation. So getting it down as small as possible is a reasonable concession. Okay, so why do this? Again, single point in time simulation can only tell us so much. If we look at September 21st at 9 a.m., 12 p.m., and 3 p.m., then we're missing quite a bit of what's going on in that space for the rest of the year. And it obviously requires an unreasonable amount of time to perform annual simulation using traditional methods where you would run 8760 simulations versus the one that sort of this annual three-phase method would provide you. Okay. So here is a quick flow chart of just radiance and all its glory and what it can do. So traditionally, we have our material and geometry preparation. So we prepare our model, and then we send it to either a point analysis for arc rays. So we're looking for how much light is falling onto a surface in lux, or we can send it to do HDRs in candelas per meter squared. So how much light is bouncing off of certain surfaces and hitting your eye. So those would be the view renders. These would be the point analyses. Now, when we go over here to the three-phase method, it can do both. But for what we've been doing here at the lab, we've been focusing mainly on the point analysis, at least for now. Our wish list is definitely to extend it to HDRs and glare analysis on an annual basis. So that is in the works. So if we look at this particular path, that's essentially what the three-phase method is. So we're preparing our model. We send it to ArcandTrib, which will generate that daylight matrix, the interaction between the sky and the outside of the window. The view matrix, interaction between the interior and the interior of the window. And then we would apply the actual weather data and the whatever complex fenestration system we would want in that particular case. And that would give us 8760 hours of data for essentially each combination of these two. So whatever fenestration system you want and whatever TMY3 climate you would like. Okay, so as far as outputs go, for each of those matrices, as you multiply the sky data by the daylight matrix, the view matrix, and the transmission matrix, we would come out of this with 8760 rows of data by however many points you have in your grid that we looked at earlier. And this, one of those grids will come out for each simulation that you do, basically, or each three-phase simulation that you do. Okay, so these matrices, again, can represent the contribution of one window group or a combination of window groups for one particular blind condition. That would be one matrix. Okay, so different operation algorithms can be applied to drive different combinations of those matrices. So if we simulate two window groups for open and closed, that would be 4 matrices. And then we would apply a logic that tells us, or blind switch A, B, or LM83 to determine what condition is window 1, what condition is window 2, and then combine those two to get our overall plot. Okay, and then this information, again, this is something I sent back to Amir as far as our workflow is concerned, and he can use the ambient operated results or the plot, the grid, to generate a fractional lighting schedule based on his zones, his EnergyPlus zones. And this is essentially how we do it. So we would take the IDF, the EnergyPlus IDF, we would parse it to essentially isolate the floors of each particular zone and see how many of the daylight analysis grid points fall within that zone. And from that point, you can either average all those points to give you an average lux in that space, or you can locate a particular sensor that you would like to control your lights, essentially. So one of those two, any would work. And this will essentially, I hope it animates. Let me see. There we go. So essentially, our scripting method would kind of go through, map each zone, isolate the analysis grid points from radiance, and then average out or pick one particular point to generate a fractional schedule for each zone separately. And then that would get output as an EnergyPlus object. And from there, we can just run or rerun an energy model based on the radiance fractional dimming schedule. And so the results may look like something like this. So if we're looking at always open, so if all the windows are open, you would see that obviously there's an abundance of light coming into the space. Inversely, if it's always closed with that shade material down, we can see there's a lot less light coming in. And just a different plot, just linear, showing a little more intensity. And when we compare the actual results, so these would be comparing always open and always closed conditions for two thresholds. So we're trying to maintain 500 lux at the work plane or wherever the grid happens to be, the analysis grid for radiance, and one for 300. So what we're seeing here is basically a 10% and a 7% difference in EUI of those two. So it definitely makes a difference. It's just a matter of does the dollar attached to it? Does that make sense to people? So, and I mean the breakdown you can see shifts quite a bit as well, mainly in the lighting, but it also does in heating here a little bit and in cooling as well. So it definitely affects the energy side. It's just a question that hasn't quite been answered yet, but how different would these results be in, I don't know, in Minneapolis, for example, versus Boise, which we ran this for Boise. So there's definitely a lot more exploration, a lot more research to be done, both on the workflow side and the application and results side. So, and with that, I'm going to open it up to questions.
I'm curious, you went from sketch of radiance to do you test everything in open studio?
The latest version, from what I understand, they were supposed to have a pretty major radiance upgrade, but we haven't really looked into it that much. We've kind of always just marched to our own beat with running Radiance and EnergyPlus text side, right? So we have basically our own scripts, R scripts and bash scripts that kind of do certain things that we need. But that's definitely on our wish list. We would like to see some of this functionality or all of it make it out to Open Studio, something like that, or even BaseSim, Viva, all those programs. So. It doesn't. So Radiance will give you numbers, and then it's up to you how you visualize them. So that was mainly our statistical analysis software. So it's free to use if you wanted to try it. So by all means. Yeah.
I do have a note here from Rob Guglielmetti at NREL. And he says, very nice. FYI, we pushed three-phase support to Open Studio just last week. We are now supporting shade controls for EnergyPlus and do a full three-phase dynamic shade simulation on the Radiance side as well, similar to what you have here. So it looks like they're growing rapidly and adding features. So
excellent. Good
for everyone to know.
Hi, Rob. He's out there. Yep. Yes.
So what we're showing here is two different light level scenarios, always open,
always closed. So essentially the always open scenario, I'd assume, is the same thing as no shading, the typical building.
Always open.
How much energy it uses, lights going all the time. And the always closed is going to assume, obviously, closed all the time, so you're going to have more lighting.
Both extremes, yeah.
Did you ever run a simulation that used your algorithms to control where those are going to be, those blinds, throughout the year?
That's actually what we're working on right now. Okay. Actually, so yeah.
Looking forward to those.
We're expecting it to fall somewhere in between these two, but you never know. It might, optimize it in some way where it's lower, or hopefully not higher. But we'll see. So,
very good. Looking forward to that.
Yeah. Yes, sir.
Have you ever come across any data on occupant performance?
Okay. So the question was, did we ever come upon any information on occupant performance? So blind operation, or?
Maybe look at the energy side, but if the occupant is able to perform a task with
I see.
a certain amount of light, the optimal amount, I guess, or temperature.
Right.
So comfort. The benefits there of regulating that temperature swing. And kind of going beyond just the energy model.
Yeah. Visually, that was the subject of our lab directors here, Kevin Vandermont Mellenberg, his PhD, his thesis. He actually did it here at this lab. There's 2 chambers in the back here, where he set up a monitoring station in one room, and then he had occupants come and go throughout the year and throughout the day, and he would perform certain tests, right? Or have them actually adjust the blinds depending on what the conditions are outside. Adjust the interior lighting based on what they just did for their blinds. So there's definitely a lot of room for not only research but just post-processing Kevin's results alone. I mean, he collected quite a bit of that. But currently, I would have to defer to him on his actual results for that portion of it. So.
We might have a couple coming in online, but I'm not sure. I do have one. I'm not totally clear on it, so I'm hoping they will clarify, but any possibility of integrated daylighting opportunity? Does that mean anything to you?
Integrated daylighting opportunity. I'm not 100% on that one.
That's what I figured.
Integrated daylighting opportunity.
I'm just not sure.
So maybe like a retrofit. Is that what, installing skylights in certain spaces, kind of like what we did here at the lab when we moved in. All these skylights were not here until we came in and put them in. So.
Okay, I do have one that just asks, can you provide some actual measurements that prove that internal shades reduce cooling load? They asked earlier, and I mentioned probably this slide was it, but maybe it's kind of hard to read. Could you point out some of those EUI numbers, or you can see on that bottom left graphic that there is variation in the cooling, but it's small.
Yeah.
So, and it's actually opposite. We're showing that always open has lower cooling than always closed. So we might have to dig into that a little more. So I guess at this point we don't have calculations for that. Would you agree?
Yes, I would.
All right, and by integrated they meant combining daylight with energy savings from the electric lighting, which I believe is what you're showing there.
Right,
so.
right, yep. But as Chris pointed out, we're sort of missing the middle condition where it's de-operated, right, compared to the 2 extremes. So work in progress, but getting there. So.
All right, well, that's all I have unless anyone else in the room has a question. Nope. All right, well, thank you, Alan and Amir.
Yep,
and we will look for more results in the future on those algorithms.
Indeed.
All right, thanks, everyone.
All right, thank you all.